Thanks very much. I'm very pleased to be here at this conference in honor of Bernard. I must confess that when the organizers of the conference invite me to give a lecture on this topic, it was not on April of last year. I don't know why I put this this date, but this was at the beginning of the summer and last year, and I have thought of different topics related to toric geometry and singularities in the work of Bernard, and finally I decided to focus on some aspects which I like it very much, but maybe are not the most recent in his work, with is more related now with valuations. But this was my choice, and so I would recall that in toric geometry we have a dictionary and transfer path between notions from in convex integral geometry on one side, and notions of algebraic geometry and commutative algebra on the other side. And I must say that Bernard has given many instances of this transfer in both directions, and also showing some results from combinatorics and leads to results in commutative algebra or algebraic geometry, and also and vice versa, using algebraic geometry results to obtain results in combinatorics. So I will start first by recalling some some facts about the isoperimetric problem, which tries to determine the relations between the volume of a compact set K in Rd and this boundary. This is a very classical problem from Greek geometry, and which we can explain in some special case when we take, for instance, the unit ball and a compact set K in R2, and we consider S its surface and L its perimeter, and then we can take a parameter T, and we consider the surface of this Minkowski sum, which is represented here. And we see from the representation that this surface can be expressed as a polynomial in T of degree 2 with coefficients S, L, and pi. And in this case, we see this relation from the figure. And in this case, the isoperimetric inequality tells us that this square of the perimeter should be bigger or equal than 4 pi, the surface of the compact set. We have this theorem of Bonnesen, which they takes from this theorem of Bonnesen tells us that if we consider this compact set K in R2, and we consider bigger the minimal ray of a circle which circumscribes the compact set, and small r the maximal ray of a circle inscribed in K, then what we have is that this number, which is nothing else than the discriminant of the polynomial in two variables, and should be bigger or equal than this difference. So if this polynomial in two variables has two real roots, and this we have this inequality here between this small r and big R. And in particular, what we get from here is that the extremal case when this quantity, this discriminant is equal to 0, may happen if and only if the small ray is equal to the big ray. So a small r is equal to the big R, so that the set K is a circle. And this is usually the hard part of these isoperimetric problems, that once we found some equality, determining when this equality holds. And this was also proven later by Bernard in using algebraic geometry methods. Now, let us come back to the notion of Minkowski sum of two sets. And so we take the sum point by point, and we have this theorem of Minkowski and Steiner, which tell us that if we take two numbers, S1 and S2, and we compute the volume of this Minkowski sum, this is expressed as an homogeneous polynomial of degree d in S1 and S2 of this form, okay? And if we write it in this form, then these coefficients are the mixed volumes of the corresponding convex sets. Yeah? And the coefficients are indexed by I and d minus y in such a way that if we make an homotopy, but these are the homogeneous, the quasi-homogeneous relation which naturally holds in this case. And in this situation, the Vd is the volume of the first one, and V0 is the volume of the second one. We can, well, in the figure here, we see the Minkowski sum of these two polygons, and V0 is the surface of the first one, V2 is the surface of the second one, and here V1 is what appears twice in the sum of these terms. So V1 is the mixed volume of these two polytopes. And now if we take two convex subsets and we make this Minkowski sum, then we get this polynomial, homogeneous polynomial in two variables. And we have again an isoperimetric inequality given by this result, that if we take the smaller given by the supremum of T, which verifies this relation, and bigger given by the supremum of T, which verifies the opposite relation, then we have this inequality, which is a generalization of the previous one when one of the compact set was a ball. Now, in order to give some idea of why one can get to this kind of relations using algebraic geometry method, I'm going to recall the toric variety determined by an integral polytope, and we take K an integral polytope that is a polytope with a vertex set in a lattice, let's say set D, for instance. Then the polytope K is determined and determines the super function, which is defined on the dual vector space by taking the minimum on the elements of the polytope. Then what we have is that there exists a fund, sigma, which subdivides this dual vector space in such a, which is consists of counts counts which are rational with respect to the dual lattice, and which is linear in restriction to the counts of sigma. Here I will suppose that the polytope has maximal dimension and so on. For each cone sigma in the fan, we have a finely generated semigroup of this form, which defines the affine normal toric variety X sigma. This semigroup is finally generated by a combinatorial argument, is Gordon's lemma. And from these affine toric varieties, we can define by gluing in a natural way a toric variety. This toric variety is compact because the fan is supported on the whole RD, and now we are going to see that this toric variety, since it's defined from a polytope, is also equipped with an invertible sheaf. Sorry. So for each cone sigma by construction, we have an integral vector m sigma such that the support function is determined on this m sigma for all vector u in sigma. And this data determines an invertible sheaf, let's call it L, on X sigma, and the place of global sections of L has a basis which is in bijection with the set of integral points of the polytope. And this shows that, this shows that the toric variety with the invertible sheaf L determines also the polytope, and we have this equality with respect to this space of global sections in terms of the integral points of the polytope. And these ideas of relating the integral points of a polytope and translate it in different ways is very important in the work of Bernard, as we will see. Now, we take two polytopes, two integral polytopes as before with the same hypothesis and with the support functions h1 and a2. So if we take the Minkowski sum of the two polytopes, we can take the dual fan associated to this Minkowski sum, and if this fan is sigma, it's going to verify that for every cone sigma in the fan, the restriction of hi to sigma is also linear for both I equal to 1 and 2. So that we get two invertible shifts, L1 and L2, as before, from H1 and H2 on the toric variety X sigma. Now we have that we can consider in a similar way if we take a couple of integers S1 and S2, then we can take the Minkowski sum, and the support function of this Minkowski sum is also linear on the cones of the fan sigma introduced before. And so we have an invertible sheaf on it, which is nothing but this tensor product of this invertible sheaf L1 and L2. And when we take we can compute this dimension, so taking this Euler characteristic, and this is, we get to computing this dimension, and this dimension is a polynomial of degree D in its S1 and S2, and if we consider the terms of degree d, we write them in this way. And what we get is that these coefficients Ri are the mixed degrees of the invertible shifts L1 and L2. Now we can compare these mixed degrees with the mixed volumes. So we have a similar writing for the volume of this Minkowski sum, as we saw before, so that we have that we can compare using this fact which relates the volume of a polytope with taking the homothésis of the polytope and counting the points. What we have is that these mixed degrees are related with the mixed volumes by this formula. And now, in this situation of toric varieties, we had a very good theory of intersection of divisors. Divisor coming from polytopes, and we have an inequality for the mixed degrees, which comes from application of the hot index theorem in this situation. And this inequality of the mixed degrees holds with equality if and only if these shifts are equivalent for some couple of integers a and b. And this is the crucial because we can deduce from the algebraic geometry that what Bernard did that an inequality for the mixed volumes. And these inequalities are exactly the Alexandrov-Fenchel inequalities, and which are obtained in this way from the application of the algebraic geometry. And the case of equality in this situation is holds if and only if there exists a couple of integers a and b such that the polytopes, the homothécy of the polytopes are equal modulo some translation. Now, these relations which were found for the integral polytopes can be extended to the case of compact convex subsets of Rd by taking into account that we can consider on this set the Hausdorff metric defined in this way, and that the mixed volumes are continued function with respect to this metric, and then we can use an approximation argument by rational polytopes by changing the lattices using refined lattices, smaller and smaller lattices, in such a way that the Alexandrov-Fenchel inequalities hold more generally in this situation for compact convex subsets. And then what we can do is relate this to the compact, to the isoperimetric inequalities. So we take K1 a compact convex subset and K2 the unit vowel. In this case, what we can find is that this mixed volume, it's expressed in terms of the volume of the boundary of K1, which we assume that so we have this relation, And then the Alexander-Fencher's inequality can be reformulated in this form. This is just a rewriting of these inequalities. And from these inequalities, we get that this power is bounded by this product. And this gives this second inequality here. Now, if in this second inequality, we have V0, Vd, which we know are the volumes of the ball and the volumes of the compact set, and Vd minus 1, which is given by the volume of the boundary. So if we substitute on the formula, what we get is an isoperimetric inequality in the case of Rd, which states this relation. In the particular case when d is equal to 2, what we get is that we recover the isoperimetric inequality which I stated before. Now we will switch to this global case to a more local situation. So first we'll recall the notion of integral closure of ideals. So we take A a commutative ring and I an ideal, and we say that an element H in A is integral over I if one half that H is satisfies these relations where the coefficients belong to the powers of the ideal I. The set of elements of the ring A, which are integral over A, define an ideal I bar, and Bernard worked very much on this notion, also in collaboration with Monique Lejeune, and it's a very interesting notion in which has a lot of different features. But well, what I recall from this work of him is that if we have an analytic algebra, then belonging to the integral closure of an ideal can be expressed as a condition in terms of all local morphisms from the ring to the ring of power series in one variable, which is given by this condition. So this means that the order of phi of H is bigger or equal to the order ideal order, the infimum of the order of the image of the elements in the ideal. What? The quotient of a power series ring by an ideal. In the case now of a monomial ideal of the power series ring, say generated by A1, AK, X, A1, AK, so A1, AK are the exponents. What we have is that we have on one side, in order to define the Newton polygon of the ideal, what we take is that we take the monomials which generate the ideal, and we take the exponent and we draw it on the plane following this idea of Newton. We add the quadrant, and this defines a set EI, and we obtain this notion of Newton polygon. So this, using this condition, what we have is that H in a series H is integral over I if and only if for all morphisms in the power series, if I put xi goes to xi of t, and if I put vi, the order of xi, then the order of the substitution is bigger or equal than this valuation. And this can be seen as a vector, as a scalar product. And this tells us that this series belongs to the integral closure if and only if the support of the series is contained in the Newton polygon. So the support of the series must be in this yellow zone in this example. Let's now recall a combinatorial theorem. It's a Carat-Theodori theorem, which I state here in some particular case. I take a connected set E in Rd, and I take B in the convex hull. Then this theorem tells us that there exists E1, Ed in I in such a way that B belongs to the convex hull of E1, Ed. Using this Carat-Theodori theorem and working a little bit combinatorially, we can prove that in our setting, if B is in the Newton polyhedron of I, then dB is in the set EI. And more generally, if we take B1, BD in an I, then this sum is in EI. Okay? And a corollary of this is a monomial, the monomial case of the theorem of Briançon-Skoda, which states in this case that if I take the integral closure and I take the power d of this ideal, then it is contained in I. And this is a particular case of a theorem of Briançon-Skoda for ideals of of the power series ring, and Bernard and following Rees has developed this theory, and this is what we are going to see now. But before, let us recall the notion of the multiplicity of a primary ideal in a local noetherian ring. We have that if I is a primary ideal, we have a Hilbert-Samuel polynomial, which is a polynomial of degree d equals to the dimension of A, and which is can be written in this form, in such a way that if I take S bigger enough, then the evaluation of this polynomial in S is just the length of this quotient. And the coefficient, normalized coefficient of this polynomial, the normalized principal coefficient of this polynomial, is the multiplicity of the ideal I. Now, if I have a monomial ideal given by this power, then we have the following. This is an elementary property which tells us that the following are equivalent, saying that the ideal is primary, or if I take the volume of the complementary of the set EI, which is what I designed here in green, this volume is finite, or that the dimension of this quotient is finite. And well, it is easy to see that the dimension of this quotient is equal to the number of points with integral coordinates in this green zone, this complement. Now we have this property that if I take an integer bigger than or equal than 1, then the number of integral points in this set defined by the power s of the monomial ideal can be translated as the number of 1 over s integral points of this other set. And this elementary observation can be used to show that this limit is exactly the Newton polygon of I, and as a consequence, in this case of monomial ideal, the multiplicity of I, of the primary ideal I, is defined by this volume up to a factor of. So this we call this the covolume of the Newton polygon. One corollary is that if I1 and I2 are primary monomial ideals, then this integral closure are equal implies that the multiplicities are equal. And secondly, if one ideal is contained into the other, then if the multiplicities are equal, then the integral closures are equal. And this is obvious from this characterization of the multiplicity, since if we have that the one Newton polygon is contained into the other and we have the equality of multiplicities, then the volumes must be equals. And if this implies, in fact, that then the Newton polygons must be equal as well, so that the integral closures must be equal too. This result is a particular case of a theorem of Ries for primary ideals in certain class of local rings. So I suppose here just to see how monomial theorems or results for monomials are a source of inspiration for commutative algebra results. Now we can I explained some similar facts for the notion of covolumes of the associated Newton polygons. So I take two primary ideal, monomial ideals with finally covolumes, and if I take two positive numbers, then this volume, this covolume, is also a homogeneous polynomial in S1 and S2 of degree D. So we can write as in the case of, similarly to the case of polytopes, but this, in this case, taking these covolumes, this has a homogeneous polynomials, and then what we get is that these coefficients of omega I are the mixed covolumes of the Newton polygons of Newton polyhedron of I1 and I2. And now we have another property which relates this mixed covolume with the notion of mixed multiplicity. If I have I1 and I2, two primary ideals of a Noetherian local ring, we have that the multiplicity of this product expressed also as an homogeneous polynomial of degree D in S1 and S2, and these coefficients EI are called the mixed multiplicities of I1 and I2. And we have, similarly as the case I stated before, Minkowski type inequality for the multiplicities, which is due to Ries and in part and to Bernard, who developed it, and which can be stated in this form. So I take a formally equidimensional Noetherian local ring of dimension D, and with a finite residue field, so some good ring, and good local ring, and I1 and I2, two primary ideals. Then we have this inequality for the mixed multiplicities, which implies this other inequality. And in particular, the first inequality is equivalent to this equality of quotients. And when this equality holds, then if the ring A is normal, we have that, writing this as a fractional number, the equality of the integral closure of ideals, which is somehow a generalization of the property I stated before in the case of monomial ideals. And this is a far generalization of this monomial case, which is not proven using combinatorial arguments, but using the singularity theoretical arguments and reducing to the case of dimension 2, if I remember well. So as a corollary, we can export the relations, because if we have these monomial primary ideals of the ring of power series, then it's easy to see that analogously as the previous case, that the mixed degrees and the mixed multiplicities are related in these forms. And we get that the mixed covolumes must satisfy these inequalities, and also the case of equalities is characterized by this equality of the Newton polygons. We can also, Bernard also have interpreted these inequalities when I take I2, the maximal ideal of the ring of power series, and I1 in Cx1, x2, then the Newton polygon of I1 can be written in a unique way as a sum of elementary Newton polygons, where an elementary Newton polygon is determined by this height and this length, horizontal and vertical. And if this is an example of how to do this, okay? And if I have that the monomial ideal I1 has this representation, then the inequality in the corollary can be written explicitly in terms of this this formula, which makes in terms of the heights and the length of the elementary Newton polygons. And the case of equality, it's also characterized when the Newton polygon of I1 should be some homothetic to the Newton polygon of I2, so some simplex of higher, homothetic to the standard simplex. Bien, in the last part of the talk, I will spoke about another subject. Is a paper with which we did some years ago, which is called toric geometry and the sample Nash modification. In this paper, we propose some material towards a general theory of toric varieties without the assumption of normality. The fact is that the toric varieties without the assumption of normality have been used in long time ago as semigroup algebras, no? But taking the coordinate rings are the semigroup of algebras of semigroup of finite type. And also in the projective case, if we have a finite set of integral points, Gelfand, Kapranov, and Selevitsky have introduced a notion of projective toric variety from the set of integral points. And in our paper, what we did is we generalized these two aspects by giving a combinatorial description in terms of a fan with attached semigroups subject to some gluing conditions. And the set of toric varieties defined by this combinatorial description is also the set of toric varieties with the classical definition where we add a condition of having a good action of the torus, and this means that the toric variety is covered by a finite subset of a finite set of invariant open subsets which are invariant for the action of the torus. In the normal case, this is the content of the Sumihiro theorem, which tells us that this condition holds, but in the non-normal case, we add this condition as an action. So, and the result is that this, with this condition is the same as the combinatorial description which we give. And the motivation was because if we have a monomial ideal in a toric variety, in an affine toric variety, for instance, and even if the variety is normal, when we do the blowing up of the monomial ideal, we don't get a normal toric variety. So we did this in order to give a combinatorial interpretation of the blowing up of a monomial ideal as a toric map in this generalized category. Then we study the sample Nash modification in the toric case. What we did here, the sample Nash modification is a canonical modification which is defined by taking the limits of tangent spaces at non-singular points. And it was a question of sample and later of Nash if the iteration of this sample Nash modification leads to a desingularization. And about this property, Gonzalez Springberg proved that in the case of torus surfaces, the iteration of the sample Nash modification followed by normalization gives a resolution of the singularities of the toric surface. And then Spivakowski proved that this holds for any normal complex toric, any normal complex surface singularity. So in our case, what we did is we gave a description of the sample Nash modification in characteristic 0 as the blowing up of a certain monomial ideal, which is the logarithmic Jacobian ideal, which appeared in fact in the case of Gonzalez Springberg, and also was also analyzed by Monique Lejeune and Ana Reguera. But we did a different proof, which is in terms of the equations, and also some Millman also gave some, say, equivalent version of this description. And then what we did is that we tried to study the iteration of the sample large modification in the toric case. And what we found is that we get some finiteness result in terms of for monomial valuations of maximal rank which dominate a point in the toric variety. And this is a local uniformization problem which tell us that if we follow this sample nabs modification, following means that at each moment I choose a chart of the toric variety determined by the evaluation. Eventually, this process stops when I take this class of valuations. And this is the content of the talk, and I have put here some of the main references with respect to toric singularities and valuations. I have to mention that I have not spoken in particular on the notion of the overweight deformations and the program to obtain local uniformization of valuations by using toric methods, because of lack, well, we have to make a choice of the subject. And but I hope that this will be the case for the next talk. And this is all. So thank you very much.
So you showed a version of a refined version of log concave inequality, which was about for the mixed volumes.
Yes.
You showed us a refined version of log concave inequality, showing that vi minus 2 minus vi minus 1 squared is bigger than some distance, some Hausdorff distance between the two. Sort of logarithmic Hausdorff distance.
Sure.
If you go back.
In the global situation, you mean?
At the very beginning, before this.
At the very beginning?
Yeah. Yeah, after this slide. Right before, I think it was, this one, the inequality below.
Yes.
This one, yeah. This works in any dimension for any.
No, this is in dimension 2.
Okay, so is there any analog of this in higher dimension? I mean,
I think there is there is a combinatorial analog of this, but not yeah.